All right, new section 2.7. We're learning about optimization in this section. Probably the single most important thing that you do with Calculus 1. It's going to involve several of the different concepts that we've learned in this class, including what we did in the previous section, where we studied this specific function. Sorry if this brings back bad memories. I feel like I did a bad job of explaining this. But in the previous section, we looked at this example where f of x equals 1/3 x minus 2 cubed minus x minus 2 squared plus 20/3, the graph that's pictured down here below. And we did lots of analysis. We figured out where this graph was increasing and where it was decreasing and where it was increasing again. We talked about where this graph was concave down, and then we also talked about where this graph is concave up. We talked about points at which the slope of the tangent line to this function was 0 at both 2 and 4. In other words, the first derivative equaled 0. And we even talked about the point at which the function switches from being concave down to concave up, the inflection point that I think ended up being at 3 if I remember right. One of those things in particular I want to focus on. It's the points at which the slope of the tangent line was equal to 0. This point here at 2 and this point here at 4. Informally, where the graph f of x gets flat. These points end up being really important, and importantly, these 2 points are very different. This first point is kind of the hilltop, if you want to think about it that way. It's the point that's higher than all of its immediate neighbors. It gets a special name. It's called a local maximum, which sort of makes sense. It's maximal, meaning higher than, all of its immediate neighbors. So I'm not saying it's higher than every point on this graph, but it's higher than all of those right around it. That's why it's a local maximum. I'll refer to it as a local maximum, but sometimes you hear books use the phrase relative maximum, so I'll throw that out here too. And that's very different than this point over here, which is lower than all of its immediate neighbors. It might not surprise you to hear that this is what's referred to as a local minimum. And again, sometimes the adjective relative is used in place of the adjective local. Anyways, these 2 points are the points that we want to study in this section. So first of all, how do we find these points? Well, again, they're points where the slope of the tangent line equals 0. And so we don't have to keep saying the slope of the tangent line equals 0. We're going to refer to those as critical points. Critical points are just points where f prime of x equals 0. Parenthetically, I'm going to add that we also have critical points where the derivative is undefined instead of equaling 0. But ignore that for now. That doesn't come into play in this example. So if we didn't have the graph, the way we'd find the critical points is we'd take this function and we'd figure out its first derivative, f prime of x, which we did in the previous video, but it never hurts to do more derivatives. We take the 1/3, it's a constant, leave it alone. Use the chain rule here by taking the 3 down in front and leaving the x minus 2 alone and subtracting 1 from the exponent. Then we'd have to take the derivative of x minus 2, which just happens to be equal to 1. And then we'd be done with the derivative of this first term and we move on to the second term, where we again use the chain rule, dealing with this exponent of 2 first, bringing that down in front and subtracting 1 from the exponent to get negative 2 x minus 2 to the first power, and then multiplying that by the derivative of x minus 2, which again is just equal to 1. Now we're done with the derivative of the second term, and we take the derivative of the third term, which since it's a constant is just equal to 0. We can clean this up a little bit by recognizing that 1/3 times 3 is just equal to 1, and 1 times 1 is 1, and 1 times x minus 2 squared is just x minus 2 squared. We can clean up this second term by rewriting it as negative 2 times x minus 2. The equation of our first derivative is x minus 2 squared minus 2 times x minus 2. To figure out our critical points, we just take that first derivative, x minus 2 squared minus 2 times x minus 2, set it equal to 0 and solve. And as we saw in the last video, one way that you can solve this is by factoring an x minus 2 from each of these terms. You're left with an x minus 2 over here, and you're left with a minus 2 over here. So we get x minus 2 times x minus 4, after using some kind of clever algebra, equals 0. So either x minus 2 equals 0, or x minus 4 equals 0. So x equals 2, and x equals 4 are our critical values. In the context of this section, that name makes a lot of sense, right? The point that we're most interested in, the critical ones, are where the first derivative equals 0, in this case 2 and 4. But the story's not over here. This was all review from the previous section. What we want to learn in this section is how to tell the difference between these 2 critical values. How can we tell whether a critical value represents a local maximum or a local minimum? And you're like, that's super easy. This one's a local maximum because it's up at the top of the hill, and this one's a local minimum because it's down at the bottom of the valley. It's like, yeah, that's true, but what if you didn't have the graph? What if we were doing this purely algebraically? Could you tell the difference between a local maximum and a local minimum? And it turns out that yes, you can, and it turns out that there's two different ways. I'm going to teach you those two different ways in this section. The first one is what's called the first derivative test. And the way you use the first derivative test is you consider the first derivative to the left of your critical value. So remember, at this critical value right here, I know the first derivative has to be equal to 0. That's what made it a critical value. But what about to the left of that point? Well, we can take advantage of the fact that we have a number line right here and use this critical value to define the region to the left of this critical value. Maybe I'll call it region 1. And since there's no critical values to the left of this critical value, region 1 extends all the way out here to negative infinity. All I have to do is figure out whether the first derivative is positive or negative in region 1. Much like we did in the last video, to figure that out, we can pick any number in region 1. So, I don't know, 1 or 0 or negative 1, whatever you want. We can test x equals, let's say, 0 by plugging it into our first derivative, f prime of x, and seeing what comes out. We have the equation of our first derivative written right here. If we change all the x's into zeros, we get negative 2 squared minus 2 times negative 2, which as we saw before is 4 plus 4, or 8. Over here in region 1, f prime of x is greater than 0. Oh yeah, that makes sense. The graph is increasing on this region. That's true, and it'll continue increasing on this region until we hit a critical value. And then at the critical value, it can change. It doesn't always change. I think it's always changed in the examples that we've seen so far, but it doesn't always change. In this case, it does, though. It starts decreasing. And it continues decreasing until we hit our next critical value. We know all that just by looking at the graph. But again, if you didn't have the graph, maybe you would call this region region 2, and you would test a number in region 2, maybe x equals 3, just to pick a nice whole number, and you'd figure out that f prime of 3 is less than 0. If you don't believe me, plug 3 into this equation. And therefore at 3, the graph is decreasing. And everywhere in region 2, the graph is decreasing. Because it can't switch from increasing to decreasing unless we're at a critical value. The only other critical value is over here at 4. So everything to the right of 4 is what I'll define as region 3. I'll test any number that I want in region 3. Maybe, I don't know, 5. F prime of 5 is going to end up being a positive number. Again, don't believe me, just plug it in up here. And that's consistent with the fact that the graph is increasing, so the first derivative is positive, to the right of 4. So if I'm just considering the first derivative goes from positive to negative, if I read this thing from left to right, at my first critical value, and it goes from negative to positive, if I'm reading this thing from left to right, at my second critical value. Think about what that means. To the left of this point, the graph is increasing. We're walking up a hill until we get to this point. And then to the right of this point, the graph is decreasing. We're walking down a hill. If we're increasing and then we stop and then we start going down, we must have a local maximum. Conversely, if we're going down, the graph is decreasing and then we hit a critical value, at which point we switch to increasing, we must be at a local minimum. We were going down, we stopped, we started going back up. That point at which we stopped must have been a minimum. That intuitive idea that we can figure out whether a critical value is a local maximum or a local minimum by looking at the change in the first derivative on either side of the critical value is what's called the first derivative test. It says if the derivative of a continuous function changes from positive to negative, think to the left of the critical value, it was going up, and to the right of the critical value, it's going down. If we're changing from positive to negative, that point where it changes must be a local maximum, as we see in this picture. And if the derivative of this function is changing from negative to positive, well, that means to the left of this point, the graph was going down. It kind of looked like this. And then at this point, it switched and started going back up. It changed from negative to positive. It must be at a local minimum. That's all the first derivative test is. It's very intuitive. It just says by looking at the first derivative, we can classify critical values as local maxima or local minima. A couple comments about the first derivative test. The first one is it's kind of annoying. The reason it's annoying is because we have to kind of test values on both sides. We have to look at this idea of how the first derivative changes. It would be nice if we could just look at the first derivative right here in the middle as opposed to the left and to the right. But we can't because we know that the first derivative right in the middle is going to be equal to 0 in both of these two cases. So a big downside to the first derivative test is you really have to consider how the first derivative is changing, and that's less than ideal. The other comment I want to make about the first derivative test is that it's entirely possible that to the left of a critical value it's positive, and to the right of a critical value it's positive. Think about what that would look like. If I have some critical value, I know my function is flat at that point. To the left of that point it's positive, that means my graph is increasing as I'm coming up to that point. But to the right of the critical value, it's also positive. That means my graph continues to increase to the right of that point. This is entirely possible that you have a critical value that is neither a minimum nor a maximum. And a nice thing about the first derivative test is it tells us that too. If the first derivative changes from positive to negative, we have a local maximum. If it changes from negative to positive, we have a local minimum. If it is positive on one side and also positive on the other side, we have neither a local minimum nor a local maximum. Similarly, if it's negative on one side and then 0, and then negative on the other side, we have neither a local minimum nor a local maximum. So big picture, we set the first derivative equal to 0 to figure out when the graph is flat. And when the graph is flat, we can either have a local maximum, a local minimum, or neither. That's how you classify critical values using the first derivative test. If you don't like that, if you don't like this idea of like sign lines and checking numbers in different regions, if all of that just kind of rubs you the wrong way, I got good news for you. There's another way you can classify local maxima and local minima, and it's what's called the second derivative test. And here's the story for the second derivative test. Notice that at this point right here, at this critical value, the shape of this function is concave down. Whereas at this point right here, this critical value, the shape of this function is concave up. That's not a coincidence. If the derivative is switching from positive to negative, that means the derivative is decreasing. If the derivative is decreasing, the second derivative is negative. So rather than look at the change in the first derivative, we can just look at the second derivative at this point. If the second derivative at this point is negative, that means my graph is concave down. If my graph is concave down at a critical value, then I must have a local maximum. Similarly, if my graph is concave up at a critical value, then I must have a local minimum. Let me show you that one in action. For the first derivative test, we needed to figure out the first derivative. Not surprisingly, for the second derivative test, we'll need to figure out the second derivative. The second derivative is just the derivative of this derivative, which is fairly easy to figure out. We got 2 times x minus 2 to the first power times the derivative of x minus 2, which is just 1, minus 2 times the derivative of x minus 2, which is just 1. If we get rid of parentheses, we got 2x minus 4 minus 2. In other words, 2x minus 6. My second derivative is 2x minus 6. With that knowledge, I can classify my critical values as local maxima and local minima. I don't have to look at points to the left and right of this critical value. I look at the critical value itself. My critical values were at 2 and 4. Let's start with the critical value at 2. If we consider the second derivative at 2, f double prime of 2, that's 2 times 2 minus 6. That's 4 minus 6. That's negative 2. Because negative 2 is less than 0, that means my function is concave down. Some people shorthand it this way, at x equals 2. I have a critical value at 2, and my function is concave down at 2. So in my head, I'm picturing kind of the flat point of this upside down bowl. I'm seeing a local maxima. Sure enough, our graph confirms that. At 2, we have a local maxima. And the exact same thing works to classify this critical value at 4 as a local minima. I just consider f double prime of 4, which is 2 times 4 minus 6, or 8 minus 6, or 2, which is greater than 0. What does that mean? It means f is concave up at x equals 2. If my graph is concave up at a critical value, I'm picturing the flat point of a right side up bowl. I'm picturing this point right here, which is a local minimum. That's the second derivative test. Typically, when students learn the first and second derivative test, they're like, oh, this is the worst. I love this thing. Second derivative test is the best. I hate this idea of having to look at both sides of my critical value. I hate having to take this number line and divide it up into regions and think about whether my first derivative is changing from positive to negative. I much prefer to just evaluate the second derivative at that point. And yeah, I do too. The second derivative test is great for a lot of reasons. The analysis for most students is easier if the derivative of a function is 0, meaning we're at a critical value, and the second derivative is negative at that point, meaning we're concave down, then that point must be a local maxima. And if the derivative of the function is 0, again, which tells us that we have a critical value, and the second derivative is positive at that point, meaning we're concave up, then that point must be a local maxima. Awesome. It's much easier to use. Where's the bad news? The bad news is we've only talked about whether the second derivative is positive or negative. What if the second derivative is 0? You're like, oh, that's easy. I remember you telling me that sometimes critical values are neither local minima nor local maxima. I bet it's the case that if the second derivative is 0, my critical value is neither a minima or a maxima. Unfortunately, no. When you're doing the second derivative test, if the second derivative is 0, the second derivative test fails. If you have a critical value at some point x, and you plug that point into your second derivative and 0 comes out, that does not necessarily tell you that that point is not a maxima or not a minima. If 0 comes out of the second derivative, the test is inconclusive. And that's the problem with the second derivative test, because students want to say that if the second derivative equals 0, it must be neither a local minima nor a local maxima. And that's entirely possible, but it's also entirely possible that you have a local maxima or that you have a local minima. The test is inconclusive if the second derivative equals 0. That sounds horrible, but it's not as bad as it seems. In practice, that case doesn't come up that much. And when that case does come up, as long as you remember that that means that this test is inconclusive, you just use your first derivative test. So not everybody does stuff this way, but me, personally, if I'm trying to classify a critical value, I always start with the second derivative test. It's easier, it's cleaner, and I hope I get a result. And typically I do. And when I say get a result, I mean I take my critical value, I put it into the second derivative, and I'm hoping that what comes out is either negative or positive. If what comes out of the second derivative is negative, I immediately know I have a local maximum. If what comes out of the second derivative is positive, I immediately know that I have a local minimum, which I just recognized it doesn't say right here, which is really annoying. I wish I had caught that earlier. But I don't want to re-record this thing. Hopefully when you were watching this, you caught that. You were thinking concave up means a right side up bowl, and the flat part of a right side up bowl is a local minimum. Anyways, when I'm using the second derivative test, that's what I'm hoping for. But if I get unlucky and 0 comes out, I just remember that that doesn't necessarily mean that I'm at neither a local minima or a local maxima. It just means I got more work to do. And then and only then do I personally use the first derivative test. The advantage of the first derivative test is it's never inconclusive. It always gives you an answer. The downside of the first derivative test is it's harder to use. The advantage to the second derivative test is it's easier to use. The downside is sometimes it's inconclusive. In case you don't believe me about this inconclusive thing, let me leave you with a really quick example. Consider the function f of x equals x to the fourth power. You may have studied this function before in like a pre-calculus class. It kind of looks like our standard parabola, but it's steeper and it kind of gets flatter down here. Loosely speaking, this is the graph of y equals x to the fourth power. The vertex of this graph is down here at 0, 0, and that's the only point where this graph gets flat, so I'd expect there to be exactly one critical value at 0. And sure enough, that's what happens. F prime of x is equal to 4x to the third power, and if I solve to find my critical values, f prime of x equals 0, I'm just solving when is 4x cubed equal to 0. I divide both sides by 4 and get x cubed equals 0. Take the cubed root of both sides of the equation, and I get x equals 0. Exactly what I thought. My critical value is right here. Is that critical value a local minimum or a local maximum? Well, clearly by looking at the graph, it's a local minimum, but what if you didn't know the graph? What you would probably do is consider the second derivative, f double prime of x. The second derivative is just as easy to figure out as the first derivative. It's just the derivative of 4x cubed, which is 12x squared. So if I'm using the second derivative test, what I'm doing is I'm taking my critical value, which is 0, and I'm plugging that into the second derivative, f double prime of 0. Well, f double prime of x is 12x squared, so f double prime of 0 is 12 times 0 squared. 0 squared is 0. 12 times 0 is 0. 0 comes out. What it means is the second derivative test is useless. It doesn't help. It doesn't allow you to classify this point. What would you do in this case? You'd switch over to the first derivative test. You'd be like, I don't want to do this, but I guess I will. First derivative test. I got my number line up here. I got one critical value at 0. So when I'm thinking about dividing my number line up into regions, I really only have two regions. Everything to the left of 0 and everything to the right of 0. If I consider any point in region 1, like, I don't know, -1, I can plug that into my first derivative, f prime of -1, and I get 4 times -1 cubed. -1 cubed is -1, and 4 times -1 is -4. What that means is f prime of -1 is negative, and since -1 is in region 1, that means f prime of x is negative for all numbers in region 1. I can do similar analysis by picking any number that I want in region 2. Maybe +1, sure. F prime of +1 is 4 times +1 cubed, which is +4. The first derivative at +1 is positive, therefore the first derivative at any number in region 2 is positive. At this critical value, my first derivative is switching from negative to positive. Therefore, per my first derivative test, that point must be a local minimum. Even though the second derivative test failed me, the first derivative test was still there to kind of save the day. If you're wondering why the second derivative test fails, I mean, it sure looks like this graph is concave up, right? We have this right side up bowl. Well, really what's going on, and there's no way you can tell this by looking at the graph, is my graph is concave up all the way over here, but ever so slightly concave up over here, and then it touches 0. And then it's concave up over on this side, all the way throughout here it's concave up. It's concave up almost everywhere, just at this point right here, it's technically 0. The second derivative is positive on this side, and it's positive on this side, and it's 0 right here. Oh, right, that's an inflection point, right? Technically, no. Even though the second derivative equals 0 right here, this is not an inflection point, because if you go back to the notes, you might see that I put in a little asterisk that said that really you only get inflection points when your second derivative switches signs. And the second derivative is positive on this side and positive on this side. It just touches 0 in between but doesn't switch signs, so it's not an inflection point. If I lost you there at the end, that's a lot of info that you don't need. What you need to be able to do in this section is classify critical values as local maxima or local minima. And I recommend that the way you do so is by using the second derivative test. And I also want to make the important point that when 0 comes out of the second derivative test, that means your second derivative test is inconclusive, but you can still use the kind of tedious first derivative test in that special case. That's everything you need for this section. All we're going to do in the next few videos is show a couple of examples of some special cases so you can see how this stuff all fits together.